What if I told you that the speed of light, the one constant we've been told is absolute, unchangeable, the bedrock of reality itself, might be nothing more than a cosmic accident? That in other universes, light could crawl like a snail, or race so fast it makes our light look frozen in time. And here's the part that should terrify you. If the speed of light in our universe were even slightly different, we're talking less than 1%, you wouldn't exist. Stars wouldn't exist. Nothing would exist. You're sitting there right now because of what might be the most improbable cosmic lottery win in existence. In the next 3 hours, I'm going to show you evidence that suggests we live in just one universe among countless others, each with its own speed of light, its own laws of physics. And most of them, almost all of them, are dead, sterile wastelands where nothing interesting can ever happen. And the kicker? Scientists are now finding ways to potentially test this. We might actually be able to prove other universes exist and measure how different their physics really are. Here's what's going to blow your mind. The speed of light isn't just about how fast light moves. It's woven into the fabric of causality itself, into the structure of space and time, into the very possibility of cause and effect. Change the speed of light, and you don't just change how fast things move, you change what can exist at all. Before we dive in, do me a favor, hit that like button and subscribe, because what we're about to explore together is going to challenge everything you thought you knew about reality. And I want to know, where in the world are you watching from? And what time is it there? Drop a comment below. I love seeing this global community come together to explore the deepest questions about existence. Let's start with something that sounds simple, but isn't. Why does light move at the speed it does? Why 299,792,458 meters per second, and not, say, twice that fast or half that slow? You've probably been told this is just the way it is, a fundamental constant of nature. But that's not an answer. That's giving up on the question. The real answer is so much stranger, and it's going to take us on a journey through quantum fields, cosmic accidents, and the possibility that reality itself is just one outcome among infinite possibilities. Think of it like this. Imagine you're born in a house and you've never left. The temperature is always 72 degrees Fahrenheit. You might think that's just the temperature, until one day you learn about other houses where people are freezing or sweltering. Suddenly, 72 degrees isn't inevitable. It's specific. It's a choice someone made when they built your house. Our universe might be like that house, and the speed of light might be like that thermostat setting, something that could have been different, and somewhere else is different. Now, I know what you're thinking. Wait, I thought the speed of light was supposed to be constant. Isn't that what Einstein proved? And you're right, in our universe, the speed of light is constant. No matter how fast you're moving when you measure it, you always get the same number. That's what makes Einstein's relativity work. But here's the twist. Einstein's theory tells us light speed is constant within our universe. It says nothing about whether other universes could have different constants. That's not a bug in the theory. It's actually pointing us towards something profound. Let me introduce you to the first scientist who's going to guide us on this journey, physicist Paul Dirac. In 1937, Dirac asked a simple but devastating question. Why do the fundamental constants of nature have the values they do? He called this the fundamental constants problem, and it's haunted physics ever since. Dirac noticed something weird. Certain numbers in physics, like the ratio between the electric force and gravitational force between two protons, come out to be huge numbers, like 10 to the 36th power. Why? Why not 10 to the 35th or 10 to the 37th? There seemed to be no reason, no explanation. It was as if someone had just picked them. This brings us to our first major revelation. The speed of light isn't actually special, because it's the speed of light. Light just happens to travel at this speed because it's massless. What's really special is something called the cosmic speed limit. the maximum speed at which causality, information, and influence can propagate through space. Light travels at this speed, but so would anything else with zero mass. Gravitational waves, for instance, travel at exactly the same speed. We're going to call this c from now on, not the speed of light, but the speed of causality. And that number, that limit 299,792,458 meters per second, is woven into the dimensional structure of space-time itself. But here's where it gets interesting. That number? It's actually arbitrary. I don't mean it's random or that it doesn't matter. I mean the number 299,792,458 is only that big because of how we defined meters and seconds. If we measured space in different units, or time in different units, we'd get a different number. What matters isn't the number itself, but how it relates to other constants of nature. It's the ratios that matter, the relationships between different fundamental constants. And those ratios? They determine what kind of universe you get. Are you still with me? Because we're about to go deeper. If you're feeling that slight vertigo, that sense that the ground is shifting under you, good. That means you're starting to see it. Reality is much stranger than you are told. So here's the foundational question we need to answer before we can talk about other universes. What exactly is the speed of light, and where does it come from? Not the number, but the actual physical phenomenon. Why is there a cosmic speed limit at all? And to answer that, we need to talk about something that sounds technical, but is actually one of the most beautiful ideas in all of physics: the structure of space-time. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would change everything. Working in Bern, Switzerland, processing patent applications by day and revolutionizing physics by night, Einstein realized something nobody else had seen. Space and time aren't separate things. They're woven together into a single fabric called space-time, and the speed of light is actually built into the geometry of this fabric. It's not that light moves fast. It's that the structure of space-time itself has a maximum rate at which influences can propagate, and that rate is what we call c. Think of it like this. Imagine space-time is like a trampoline. When you place a bowling ball on a trampoline, it creates a dip, a curve in the fabric. Other objects roll toward that. That's what we call gravity. But here's the key. When you move the bowling ball, the information about that movement doesn't instantly affect the entire trampoline. The ripple travels outward at a specific speed, determined by the tension and elasticity of the trampoline fabric. That speed is c. Change the fabric, change its tension, its elasticity, and you change the speed of the ripple. Change space-time's properties, and you change c. But what determines space-time's properties? What sets that tension and elasticity? This is where things get wild, because the answer comes from something called quantum field theory, and it's going to sound like science fiction. The properties of space-time are determined by something called the vacuum energy, the zero-point energy of quantum fields that permeate all of space. Even empty space isn't empty. It's seething with quantum fields, and these fields have energy even at their lowest possible state. That vacuum energy creates a kind of stiffness to space-time, and that stiffness determines c. Now here's the revelation that's going to set up everything else. In quantum field theory, which was developed throughout the 1930s, 1960s by physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. They shared the Nobel Prize in 1965 for this work. The vacuum energy is determined by the properties of the fields themselves. Change the fields, and you change the vacuum energy. Change the vacuum energy, and you change the properties of space-time. Change the properties of space-time, and you change c. And here's where your mind should start bending. Quantum field theory doesn't tell us what the properties of these fields must be. The masses of particles, the strengths of forces, the value of c, these are what physicists call free parameters. They're numbers you have to plug into the equations. Numbers that the theory itself doesn't predict or explain. They're just ... given input values. And theoretically, they could be different. Let me paint you a picture of what this means. Imagine you're playing a video game. The game has a physics engine that determines how objects move, how forces work, how fast light travels in the game world. Now imagine the game developers could go into the code and change some numbers. Make gravity stronger, make friction lower, make the speed of light faster. Each set of numbers creates a different possible game world with different physics. Some combinations might make the game unplayable. Maybe everything moves so fast you can't see it, or gravity is so strong nothing can move at all. But some combinations work, creating stable, interesting game worlds. Our universe might be like that. The laws of physics, the mathematical structure, the equations might be fixed, like the game engine's code. But the constants in those equations, the specific numbers like c, the strength of gravity, the mass of electrons, might be adjustable parameters. And if they can be adjusted, then somewhere in the vast space of possibilities, they are adjusted. Other universes might exist with different settings, different values for these constants. This isn't wild speculation anymore. This is the multiverse hypothesis, and it's being taken seriously by some of the most respected physicists in the world. But before we get to other universes, we need to understand something crucial. Why does our universe have the specific speed of light it has? Why this value and not another? And here's where we encounter our first major obstacle to understanding. We don't know. That's not me being evasive. That's the honest scientific answer. We can measure the speed of light to incredible precision. We can see how it's connected to other constants through the equations of quantum field theory. We can observe that it's constant everywhere we look in our universe, at every moment in cosmic history. But we cannot explain why it has the value it does. It's like finding a combination lock already opened and realizing you have no idea what the combination was. You just know it worked. But here's what we do know, and this is going to blow your mind. If the speed of light were different, even a tiny bit different, the universe would be radically, unrecognizably different. We can calculate what would happen. We can model it. And what we find is that we exist on a knife's edge of possibility, in a universe tuned so precisely that it's almost impossible to believe it's an accident. Let me give you a specific example, and I want you to really sit with this. The speed of light determines how fast electromagnetic interactions happen. Those interactions are what hold atoms together, what allow chemistry to work, what make molecules possible. If c were about 10% faster, the electromagnetic force would be stronger relative to gravity. Electrons would orbit atomic nuclei more tightly. Atoms would be smaller and heavier. Stars would burn differently, much hotter and faster. A star like our sun would exhaust its fuel in a few million years instead of 10 billion years. There wouldn't be time for complex chemistry to develop, for planets to cool, for life to evolve. You wouldn't exist. But what if c were slower? Then electromagnetic interactions would be weaker. Atoms would be larger and more fragile. Chemical bonds would be weaker. Complex molecules like proteins and DNA might not be stable enough to exist. Water might not have the bizarre and wonderful properties it does, properties that are essential for life as we know it. Again, you wouldn't exist. This is called the fine-tuning problem, and it's one of the biggest mysteries in modern physics. Our universe appears to be fine-tuned for complexity, for structure, for life. The constants of nature seem to be set within very narrow ranges that allow interesting things to happen. Outside those ranges, you get sterile, boring universes where nothing happens, where nothing can happen. And this brings us to the question that's going to drive everything else in this video. Is this fine-tuning evidence of design, of a creator who set the dials just right? Is it just an incredible coincidence? A one-in-infinity lucky break? Or is it evidence of something else, entirely a multiverse, where every possible value of every constant exists somewhere. And we find ourselves in one of the rare universes that can support observers, simply because universes that can't support observers have nobody in them to wonder about it. That last possibility, it has a name. It's called the anthropic principle, and it was articulated in its modern form by physicist Brandon Carter in 1973. Carter was addressing a conference on cosmology when he made a simple but profound observation. The fact that we exist to observe the universe means we necessarily find ourselves in a universe capable of producing observers. It's a selection effect. You can't find yourself in a dead universe because dead universes don't produce observers. So no matter how improbable our universe seems, the fact that we're here to be surprised by it is itself an explanation, if there are many universes with different properties. But Carter went further. He divided the anthropic principle into weak and strong versions. The weak anthropic principle just says we observe the universe to be compatible with our existence. Because we exist, that's just logic. The strong anthropic principle says the universe must have properties that allow observers to develop at some point because, well, here's where it gets controversial. Some versions suggest it's because consciousness or observation is somehow fundamental to reality. Others suggest it's because there are many universes, and observer-supporting universes will necessarily be observed. Are you starting to see how deep this rabbit hole goes? We started with a simple question. Do other universes have different light speeds? And we've already encountered quantum fields, the structure of space-time, the fine-tuning problem, and the anthropic principle. And we're just getting started. Let me give you a moment to catch your breath, because in the next section, we're going to dive into the evidence that other universes might actually exist. Not philosophical speculation, but actual scientific theories and observations that point toward a multiverse. We're going to meet the physicists who are working on this right now today, and we're going to see how the speed of light in those other universes might be utterly different from ours. But before we move on, I want you to think about something. You're sitting there, in a universe with a specific speed of light, a specific set of physical constants, wondering if things could be different elsewhere. The fact that you can ask that question, that you exist to ask it, might itself be part of the answer. You're not separate from this mystery. You're a consequence of it, an expression of it. The universe isn't just something you observe. It's something you're made of, something you participate in. And that participation, that existence, is only possible because the cosmic dice came up just right. In the next section, we're going to explore the first major evidence for the multiverse, eternal inflation. We're going to see how the earliest moments of cosmic history might have spawned an infinite number of universes, each with its own physics, its own speed of light. And we're going to meet the physicist who's been called both a genius and a heretic for proposing this idea, a Russian scientist whose work has transformed cosmology, and who, as of my last knowledge update in January 2025, is still actively researching these questions. So let's talk about how universes are made. And I don't mean that as a metaphor. I mean the actual physical mechanism by which universes come into existence, branch off from each other, create isolated domains of spacetime with potentially different physical laws. This isn't philosophy anymore. This is cosmology, a scientific study of the origin and evolution of the cosmos, and it's based on real observations, real data, and real mathematics. To understand this, we need to go back to the very beginning, not just the beginning of our universe, but the mechanism that might have created countless universes. We need to talk about cosmic inflation, one of the most successful and well-supported theories in modern cosmology. But more than that, we need to talk about what happens when inflation doesn't stop cleanly, when it goes on forever in some places while ending in others. This is called eternal inflation, and it's the first major pathway to a multiverse with varying physics. Here's the story. In the early 1980s, a young physicist named Alan Guth was thinking about a problem in cosmology called the horizon problem. The universe looks remarkably uniform in all directions. The cosmic microwave background radiation, the afterglow of the Big Bang, has almost exactly the same temperature no matter where you look, to within 1 part in 100,000. But here's the puzzle. According to standard Big Bang cosmology, regions of space on opposite sides of the observable universe should never have been in contact with each other. They're too far apart. Light hasn't had time to travel between them in the 13.8 billion years since the Big Bang. So how did they agree to have the same temperature? How did they equilibrate if they could never communicate? Guth's solution, published in 1981, was inflation. A brief period in the universe's first fraction of a second when space expanded exponentially, far faster than light speed. This wasn't light moving faster than c. This was space itself stretching, carrying everything in it along for the ride. And there's no speed limit on how fast space can expand. During this inflationary period, a tiny region of space, smaller than an atom, expanded to become larger than the currently observable universe. That tiny region was in thermal contact. All its parts could communicate before inflation started. Then inflation blew it up to cosmic scales while preserving its uniformity. Think of it like this. Imagine you draw some dots on a deflated balloon, dots that are close together. The dots can communicate. They're in contact. Now inflate the balloon rapidly. The dots move apart, but they still have the same color, the same properties, because they started together. That's inflation solving the horizon problem. The universe looks uniform because all its parts came from a tiny region that was uniform before inflation kicked in. But here's where it gets wild. Guth's original inflation model had a problem. Inflation was supposed to start and then stop, allowing the energy driving inflation to convert into matter and radiation, the stuff of the Big Bang. But the more physicists studied the mathematics of inflation, the more they realized something disturbing. Inflation doesn't want to stop. Or rather, it doesn't stop everywhere at once. The field that drives inflation, called the inflaton field, has quantum fluctuations, random jitters at the quantum level. In some regions, those fluctuations cause inflation to end, and a bubble of post-inflationary space forms a universe like ours. But in other regions, the fluctuations push the inflaton field in the opposite direction, and inflation continues. This was realized in the mid-1980s by physicist Andrei Lind, working at the Lebedev Physical Institute in Moscow. Lind proposed what he called eternal inflation, or chaotic inflation. Here's how it works. Imagine a landscape with hills and valleys. The inflaton field is like a ball rolling across this landscape. When the ball is on a high plateau, inflation is happening. Space is expanding exponentially. When the ball rolls down into a valley, inflation ends in that region and a universe forms. But the landscape is bumpy, with quantum fluctuations constantly kicking the ball around. In most places, the ball gets kicked up, not down, because space is expanding so fast. For every region where inflation ends, multiple new regions spawn where inflation continues. Inflation becomes self-reproducing, eternal. It never globally ends. It just creates an infinite number of bubble universes, each being a post-inflationary region surrounded by eternally inflating space. Now here's the part that's going to blow your mind. Lind and others realized that these bubble universes don't all have to be the same. The valleys in the landscape, the stable states where inflation ends, might correspond to different possible configurations of the fundamental fields, different vacuum states of quantum field theory. Each valley might have different values for the physical constants, different particle masses, different force strengths, and yes, potentially different values for the speed of light. This landscape of possible universes isn't just theoretical speculation. It emerges naturally from string theory, the leading candidate for a unified theory of quantum mechanics and gravity. In string theory, which gained prominence in the 1980s and 90s through the work of physicists like Leonard Susskind, Ed Witten, and others, The fundamental constituents of reality aren't point particles, but tiny vibrating strings. Different vibration patterns of these strings correspond to different particles. But string theory requires extra dimensions of space beyond the 3 we experience, typically 6 or 7 extra dimensions, curled up so small we can't perceive them. Here's the key. The way these extra dimensions curl up determines the physics of the resulting 4-dimensional universe, 3 space dimensions plus time. Different curling patterns, different compactifications, give different values for the constants of nature. And string theorists discovered something shocking. There are a lot of possible compactifications. Not thousands, not millions. Estimates suggest there might be 10 to the power of 500 different possible configurations. That's more possible universes than there are atoms in the observable universe. Way more. That's more than all the atoms that could fit in a billion observable universes. This vast collection of possible universes is called the string theory landscape, and it was characterized most clearly by Leonard Susskind in the early 2000s. Susskind, a professor at Stanford who had been one of the founders of string theory back in the 1970s, realized that if string theory and eternal inflation are both correct, then we're forced into a picture of reality that includes this vast multiverse. Each bubble universe in eternal inflation corresponds to some point in the string landscape with its own values for the constants of nature. And yes, that includes the speed of light. But wait, I told you earlier that C is woven into the structure of spacetime itself. If you change C, aren't you changing spacetime? Yes, exactly. Different bubble universes don't just have different constants. They have different spacetime geometries, different vacuum energies, different underlying structures. The fabric of one universe might be completely different from the fabric of another. It's not like they're different patterns on the same fabric. They're different fabrics entirely. Think of it like this. Imagine universes as different materials: steel, rubber, water, air. Each material transmits sound at a different speed because each has different properties. The speed of sound isn't universal. It depends on the medium. Similarly, each universe has its own space-time medium, and the cosmic speed limit, what we call c in our universe, depends on that medium's properties. In universes with different vacuum energies, different configurations of quantum fields, c would be different. Not because light itself changed, but because the underlying structure of space-time is different. Are you feeling it yet? That vertigo, that sense of the ground falling away? Good, because we're approaching a revelation that's going to reframe everything. The speed of light in our universe, 299,792,458 meters per second, might not just be arbitrary. It might be one of a very small set of values that allow for complex structure, for stars, for planets, for life, for observers. And we find ourselves in a universe with this value, not because it's special in some cosmic sense, but because universes with wildly different values don't produce anyone to ask the question. This is the anthropic principle in action. But now it's not just a philosophical idea. It's a testable scientific hypothesis, at least in principle. If the multiverse is real, if other bubble universes exist with different physics, then the constants of nature in our universe should be typical of universes that support observers. Given the distribution of constants across the landscape, we can calculate what range of constants allows for complexity and compare that to what we observe. If our constants fall within the range that allows observers, but are otherwise typical or random within that range, that's evidence for the anthropic explanation. If they're special even within the observer-supporting range, that might point to something else design, or a mechanism we don't understand yet. And here's the stunning thing. When physicists have done these calculations for various constants, they find that our universe is indeed near the edge of the observer-supporting range for many parameters. Not always in the middle, safely away from danger, but often close to the boundaries. It's as if we're in one of the marginal universes, one that just barely allows complexity. That's actually what you'd expect from the anthropic principle. Most observer-supporting universes would be near the edges of possibility because there's more landscape space there. The safe middle would be rare. But let me give you a specific example with the speed of light, because this is where things get really concrete. The electromagnetic force strength is directly related to c through a dimensionless constant called the fine structure constant, usually denoted as alpha. Alpha is about 1/137th, and it determines how strongly electrons and photons interact. If c were different, but other constants stayed the same, alpha would change. Make c faster, and alpha gets smaller, electromagnetic interactions become weaker. Make c slower, and alpha gets larger, electromagnetic interactions become stronger. Now, here's the remarkable thing. If alpha were more than about 10% larger than its current value, stellar nucleosynthesis, the process by which stars create heavy elements, would fail. Stars wouldn't produce carbon, oxygen, nitrogen, iron, all the elements essential for chemistry and life. The universe would have only hydrogen and helium. If alpha were more than about 10% smaller, you'd have the opposite problem. Complex atomic orbitals might not be stable. Chemistry would be radically different or impossible. And again, life as we know it couldn't exist. We sit in a narrow window, and that window is defined by the value of c, along with other constants. Change c, and you step outside that window. So the speed of light in our universe isn't arbitrary. It's constrained by the requirement that observers exist. In other bubble universes, where there are no such observers, c could be radically different. Those universes exist in the multiverse, but they're empty, sterile, boring. Nobody's there to measure anything. Does this explanation satisfy you? Or does it feel like a cheat, like we're saying, it is what it is, because if it weren't, we wouldn't be here to ask? I get that reaction. It bothered physicists too, especially at first. It feels unsatisfying, like it's giving up on finding a deeper explanation. But here's the thing. If the multiverse is real, then the anthropic explanation isn't giving up. It's recognizing the reality of the situation. It's like asking, why am I alive in the 21st century? And answering, because if I were alive in the 12th century, I'd be a different person. That's not a deep answer, but it's also not wrong. You exist when you exist, and observers exist in observer-supporting universes. The real question is, can we test this? Can we find evidence that the multiverse is real? That other universes with different speeds of light actually exist? And the answer is, maybe. There are several proposed ways, and while they're speculative, they're not science fiction. They're based on serious physics, and people are actively working on them. First, we could look for collisions between bubble universes. If our universe, our bubble in the eternally inflating expanse, collided with another bubble universe in the distant past, it might have left a mark on the cosmic microwave background radiation. Imagine two soap bubbles merging. There's a line, a seam where they join. In cosmology, a bubble collision would create a distinctive pattern in the CMB, a disk-shaped anomaly with specific statistical properties. Physicists, including a team led by Matthew Kleban at New York University, have calculated what these collision signatures should look like and have searched for them in CMB data from the Planck satellite. As of my knowledge cutoff in January 2025, no definitive collision signatures have been found, but the search continues with ever more sensitive instruments. Second, we might observe variations in the fundamental constants across space or time. If the boundaries of our bubble universe are not perfectly smooth, or if our universe is transitioning toward a different vacuum state, we might see the constants of nature changing slightly from place to place or over cosmic history. Astronomers have looked for variations in the fine structure constant by observing distant quasars' light from billions of years ago passing through clouds of gas. Some controversial results in the early 2000s suggested a tiny variation in alpha, but subsequent observations have been consistent with no change. Still, the search continues, and more precise measurements might yet reveal something. Third, and most speculatively, we might someday develop quantum theories of gravity that predict the probability distribution of constants across the landscape. If we could calculate how common universes with our value of C are versus universes with very different values, and if that distribution matched our anthropic predictions, that would be powerful indirect evidence. This is far beyond our current capabilities, but string theory and related approaches are working towards such calculations. So where does this leave us? We've explored eternal inflation, the string landscape, and the anthropic principle. We've seen how the multiverse hypothesis provides a framework for understanding why the speed of light has the value it does. Because we exist in one of the bubble universes, where C allows for complexity and observers. Other bubbles exist with different values of C, but they're empty, so nobody's there to measure anything different. But I want to pause here and acknowledge something. This might feel unsatisfying to you. It might feel like we've replaced one mystery, why is C what it is, with a bigger mystery, why is there a multiverse? And you're right to feel that way. The multiverse hypothesis doesn't eliminate mystery. It transforms it. Instead of asking, why this universe? We're asking, why a multiverse? And why these rules for generating universes? We've pushed the question back, but we haven't made it disappear. Some physicists love this. They see the multiverse as a natural consequence of well-established theories, inflation and string theory, and they embrace the anthropic explanation as elegant and sufficient. Others hate it. They see the multiverse as unscientific, unfalsifiable, a surrender to the hard work of finding deeper explanations. The debate is fierce, and it's ongoing. This is science in action, grappling with the deepest questions about reality. And here's what's beautiful about this moment in history. You're alive while this is being figured out. These aren't questions from dusty textbooks. These are active research areas. Papers are being published right now, as we speak, exploring these ideas. Experiments are being designed. Observations are being made. The answer to, do other universes have different light speeds? Might be settled in your lifetime. Think about that. In the next section, we're going to explore another pathway to the multiverse, one that's even stranger than eternal inflation. We're going to talk about quantum mechanics and the many worlds interpretation, and we're going to see how every quantum event might create branching universes. But here's the twist. In the quantum multiverse, the speed of light is the same across all branches, because they all descend from the same parent universe with the same laws. So we're going to have to dig deeper and ask whether quantum tunneling or vacuum decay could change the fundamental constants within the quantum multiverse. This is going to get wild. But before we go there, take a moment. Like this video if you're still with me, and drop a comment about what you're thinking right now. Are you leaning toward the multiverse being real? Does it seem like a cop-out? Are you excited, terrified, confused? Let me know. And make sure you're subscribed, because the next section is going to challenge everything we've discussed so far. The journey continues. Let's keep going. Now we need to talk about quantum mechanics, and I promise you, this is going to mess with your head even more than eternal inflation did. Because quantum mechanics suggests another kind of multiverse, one where the speed of light is the same everywhere at first. But then things get complicated, and we're going to see how even in a quantum multiverse, you might end up with regions of reality where the fundamental constants, including C, are radically different. Let me start with something that's going to sound absurd. According to one interpretation of quantum mechanics, arguably the most straightforward interpretation, every time a quantum event happens, the universe splits into multiple branches, one for each possible outcome. This isn't metaphorical. This is a literal claim about the structure of reality, proposed by physicist Hugh Everett III in his 1957 doctoral thesis at Princeton. It's called the many worlds interpretation, and while it was initially dismissed as crazy, it's now taken seriously by a significant fraction of quantum physicists. Some estimates suggest that among physicists who work on quantum foundations, many worlds might even be the most popular interpretation. Here's how it works. In quantum mechanics, before you measure something, it exists in a superposition multiple states at once. The famous example is Schrodinger's cat, simultaneously alive and dead until you open the box. The standard Copenhagen interpretation says that measurement collapses the superposition into one outcome or the other. But here's the problem. Collapse is not described by the Schrödinger equation, the fundamental equation of quantum mechanics. Collapse is added by hand, an extra rule that says quantum mechanics stops working when measurements happen. That's weird. Why should measurements be special? What counts as a measurement? It's led to decades of philosophical confusion. Everett's solution was radical. Forget collapse. Take the Schrödinger equation literally and let it apply to everything, including the measuring device and the physicist. When you measure a quantum system, you don't collapse it, you get entangled with it. The combined system of you plus cat enters a superposition. One branch where you see the cat alive, another branch where you see the cat dead. Both branches exist in the universal wave function, but each branch is unaware of the other because they've decayed. They no longer interact quantum mechanically. From your subjective experience, it feels like one outcome happened, but objectively, both did in different branches of reality. Think of it like this. Imagine reality is like a tree, constantly branching. Every quantum event is a split, creating new branches. You personally follow one particular path through the tree, experiencing one sequence of outcomes. But other versions of you follow other paths, experiencing different outcomes. All branches are equally real. You just can't perceive the others because decoherence has separated you from them. Now, here's the key question. In the many worlds interpretation, do the fundamental constants of nature vary between branches? And the answer is, not usually no. All branches descend from the same quantum state with the same Hamiltonian, the same energy function describing the physics. The speed of light is the same in all branches because they all share the same underlying laws of physics. When the universe branches at a quantum event, it's branching in terms of which outcome happened, not in terms of what the laws of physics are. So if many worlds is correct, does that mean there aren't other universes with different speeds of light? Well, hold on. Because there's a deeper question. Could the quantum state of the universe itself include superpositions over different values of the fundamental constants? Could the initial conditions at the Big Bang have been a quantum superposition that included different possible laws of physics? And could the many worlds branching have selected different physical constants in different branches? This is where quantum cosmology enters the picture, and it's some of the most speculative but fascinating physics being done today. Quantum cosmology tries to apply quantum mechanics to the universe as a whole. The idea is that the universe's wave function describes not just the positions and states of particles, but the configuration of space-time itself, including the values of the fundamental constants. If the early universe was in a quantum superposition of different field configurations, different vacuum states, then many worlds branching could have produced different branches with different physics. This was explored in the 1980s and 90s by physicists like James Hartle and Stephen Hawking. In 1983, they proposed what's called the Hartle-Hawking no-boundary proposal, a quantum mechanical description of the universe's birth. In their framework, the universe doesn't have a beginning in time. Instead, time itself emerges from a more fundamental quantum description. And in that quantum description, the early universe could have been in a superposition over many possible configurations, including configurations with different values for constants, like the speed of light. But here's where things get really mind-bending. If this is true, then the quantum multiverse and the inflationary multiverse might be the same thing, just described in different languages. The eternal inflation picture talks about different bubble universes in different regions of space. The quantum cosmology picture talks about different branches of the universal wave function. But these might just be two ways of describing the same underlying reality. The bubbles might be the branches. Different branches of the wave function might correspond to different inflationary outcomes, different vacuum states, different values of C. This is called quantum eternal inflation, and it's been developed by physicists like Andre Linde, who we met earlier, working with Vade Venturin and others in the 2000s and 2010s. In this picture, the multiverse is both quantum and inflationary. Quantum branching produces different inflationary histories, and different inflationary histories produce different bubble universes with different physics. It's a synthesis of both approaches, and it suggests that yes, in the full quantum description of reality, there are indeed branches, worlds, universes, whatever you want to call them, where the speed of light is different. But let me give you an even more concrete mechanism for how the speed of light could change, one that doesn't require speculating about the quantum state at the Big Bang. I'm talking about something called vacuum decay or false vacuum tunneling. This is where quantum mechanics allows for spontaneous changes in the fundamental constants, even in our universe right now. Here's the concept. The vacuum state of our universe, the lowest energy configuration of all the quantum fields, might not actually be the true lowest energy state. It might be what's called a false vacuum, a metastable state that looks stable, but could suddenly transition to a lower energy true vacuum through a process called quantum tunneling. Think of a ball sitting in a shallow bowl on the side of a hill. The ball is stable in the bowl, it won't roll out on its own. But if you give it enough of a push, or if it randomly quantum tunnels through the bowl's wall, it could roll down to a deeper valley below. That's the true vacuum, the actual lowest energy state. If our universe is in a false vacuum, then somewhere, at some random time, a bubble of true vacuum could spontaneously form through quantum tunneling. This bubble would expand at the speed of light, converting false vacuum to true vacuum. And here's the kicker. Inside that bubble, the physics would be different. The vacuum energy would be different. The properties of quantum fields would be different. And yes, the speed of light, the cosmic speed limit, would be different. This isn't just theoretical speculation. This is taken very seriously as a possible fate for our universe. In 2012, when the Higgs boson was discovered at the Large Hadron Collider, physicists calculated something disturbing. Given the measured mass of the Higgs boson, about 125 GeV, and the measured mass of the top quark, our universe appears to be in a metastable vacuum state. We're living in a false vacuum. The true vacuum is lower in energy, and someday, maybe tomorrow, maybe in 10 to the 100 years, a bubble of true vacuum could nucleate and destroy everything we know. Now, before you panic, let me be clear. The timescale for this is likely much, much longer than the current age of the universe. The probability of it happening anytime soon is vanishingly small. But the point is, it's possible. Quantum mechanics allows it. And if it happens, the interior of that bubble would be a region of space-time with different fundamental constants, including a different speed of light. Think about what this means. Even if we don't have access to other universes in the eternal inflation multiverse, even if many worlds branching doesn't produce different constants, we could still have regions of space-time pockets within the quantum vacuum where C is different. These pockets would be separated from us by an expanding bubble wall moving at light speed so we could never see them coming. They'd hit us without warning, and we'd be converted to the new vacuum with new physics before we knew what happened. Sidney Coleman, a legendary theoretical physicist at Harvard who passed away in 2007, worked out the mathematics of vacuum decay in the 1970s and 80s. His work, particularly a 1977 paper titled Fate of the False Vacuum, showed how quantum tunneling could destroy a metastable universe. Coleman calculated that the bubble of true vacuum would expand at exactly the speed of light, or more precisely, at the value of C in the false vacuum outside the bubble. Inside the bubble, once the new vacuum was established, there would be a new space-time structure, potentially with a different cosmic speed limit. Are you feeling it? The existential dread? The realization that the universe you live in might be temporary, metastable, balanced on a knife's edge? Good, because this is real physics, based on quantum field theory and general relativity, and it points to a profoundly unstable cosmos. We live in a universe that might be one quantum fluctuation away from complete transformation. But here's the twist that should actually comfort you. If vacuum decay is possible, it's almost certainly already happened, many times in the vast expanse of the eternally inflating multiverse. Some bubble universes are born in false vacuums and later decay to true vacuums. Some are born directly in true vacuums. Some might go through multiple stages of decay, transitioning through several vacuum states. And in each state, the speed of light would be different. So now we have multiple mechanisms for different light speeds in different universes. Eternal inflation, creating different bubble universes with different vacuum states. Quantum branching potentially creating different branches with different field configurations. And vacuum decay creating transitional regions within a single spacetime where the constants change. All of these mechanisms might be aspects of the same underlying reality, different facets of the multiverse. Let me introduce you to another key figure in this story, physicist Frank Wilczek, who won the Nobel Prize in 2004 for his work on the strong nuclear force. Wilczek has written extensively about what he calls the lightness of being, the mystery of why the fundamental constants have the values they do, and why the vacuum energy is so small. In a 2006 paper, Wilczek explored how quantum corrections to the vacuum energy could lead to a landscape of possible vacuum states, exactly the kind of landscape that eternal inflation and string theory predict. His work connects quantum field theory, cosmology, and the multiverse in a rigorous mathematical framework. Wilczek points out something profound. The vacuum of quantum field theory is not empty nothingness. It's a dynamical medium, seething with quantum fluctuations, with virtual particles constantly appearing and disappearing. This medium has properties energy density, pressure, stiffness, and these properties determine the fundamental constants. Change the vacuum state, and you change the medium. Change the medium, and you change everything, including C. Think of it like this. Imagine you're a sound wave. Your speed depends on the medium you're traveling through: air, water, steel. To you, the speed of sound is a fundamental constant, the maximum speed at which you can propagate information. Now imagine there are different regions of space filled with different media. In each region, the speed of sound is different. That's what different vacuum states are like. Different media for the propagation of influences, with different cosmic speed limits. And here's what's going to blow your mind. We might actually be able to observe evidence of different vacuum states in the cosmic microwave background. If our observable universe formed in a region that transitioned between vacuum states during inflation, there might be subtle patterns in the CMB that reveal this transition. Physicists are actively searching for these signals. The Planck satellite data, released in final form in 2018, provided the most detailed map of the CMB ever made, and teams of researchers are still analyzing it for anomalies that might point to multiverse physics. But let me address something you might be thinking. If all of this is true, if there are countless universes with different speeds of light, does that make our universe less special? Does it diminish the wonder? The feeling that there's something meaningful about existence? I would argue the opposite. The fact that you exist in this particular universe, with this particular value of C, is extraordinary. The odds against it are astronomical literally. If the landscape has 10 to the 500 possible vacuum states, and only a tiny fraction of them support complexity and life, then you're experiencing something incredibly rare. Not unique, there are presumably many other observer-supporting universes out there, but rare, special, improbable. And here's the deeper point. The multiverse doesn't make your existence meaningless. It makes it contingent. You exist because of a specific set of initial conditions, a specific path through the cosmic landscape, a specific sequence of quantum events. Change any of those, and you wouldn't be here. That's not depressing. That's profound. It means your existence is a concrete, specific fact about the structure of reality, not an abstract necessity. You're here because of how things actually unfolded, not because you had to be here. In fact, I'd argue that the multiverse makes existence more meaningful, not less. If our universe were the only possible universe, if the constants had to be what they are, then existence would be inevitable, automatic, devoid of contingency. But if our universe is one possibility among countless others, then the fact that this possibility was realized, that this particular configuration exists, that you exist within it, is genuinely remarkable. But we're not done yet. Because I've been talking about other universes as if they're separate from ours, disconnected, inaccessible, and in most multiverse scenarios, that's true. We can't travel to other bubble universes. They're beyond our cosmic horizon. We can't access other quantum branches. Decoherence has separated us from them. But what if I told you there might be ways to probe other universes, to detect their influence, or even speculatively to communicate with them? In the next section, we're going to explore the most cutting-edge research on multiverse detection. We're going to talk about gravitational waves from bubble collisions, quantum entanglement across branches, and even the possibility of sending information through wormholes to other universes. We're going to meet the physicists who are designing experiments right now to test these ideas. And we're going to confront a question that should terrify and excite you in equal measure. What if we're already receiving signals from other universes, and we just don't know how to recognize them? Stay with me, we're going deeper. So let's talk about evidence. Not philosophical arguments, not mathematical possibilities, but actual, concrete ways we might detect the existence of other universes with different speeds of light. Because if the multiverse is real, it shouldn't just be an untestable hypothesis. There should be observable consequences, fingerprints left on our universe by the existence of others. The first place to look is the cosmic microwave background, the CMB, the oldest light in the universe. This radiation was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. The CMB is remarkably uniform, almost the same temperature in every direction, but it has tiny fluctuations, variations of about 1 part in 100,000. These fluctuations are the seeds that grew into galaxies, clusters, and the large-scale structure we see today. But here's what's interesting. The pattern of these fluctuations encodes information about the early universe. The size, shape, and statistics of the hot and cold spots tell us about the physics of inflation, the density of matter and energy, the curvature of space. And if our universe collided with another bubble universe during or after inflation, that collision should leave a distinctive signature in the CMB. Here's how it would work. Imagine two bubbles of post-inflationary space expanding into the eternally inflating background. If they touch, there's a collision. The collision releases energy at the interface, creating a shockwave that propagates into both bubbles. In our universe, this shockwave would appear as a circular feature in the CMB, a disc-shaped region with specific statistical properties. The center of the disc would mark the direction of the collision, and the disk's size would depend on when the collision happened and how far away it was. In 2007, physicists Ben Freivogel, Matthew Kleben, Alberto Nicolis, and Chris Sigurdsson published a paper calculating exactly what these collision signatures should look like. They showed that collisions would create both temperature fluctuations and polarization patterns in the CMB, with distinctive correlations that don't appear in standard cosmology. Since then, multiple teams have searched CMB data for these signatures. The most thorough search to date used data from the Planck satellite, which mapped the CMB from 2009 to 2013 with unprecedented precision. In 2016, a team including Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris published results from a comprehensive search for bubble collision signatures in the Planck data. Their conclusion? No definitive collisions detected, but several interesting anomalies that could potentially be collision candidates. The statistics weren't strong enough to claim a discovery, but they were intriguing enough to warrant further investigation. Think about what this means. We've actually looked for other universes. We've analyzed real data, searching for evidence of collisions with other bubbles in the multiverse. We haven't found proof yet, but we've set constraints. If bubble collisions happened in our cosmic history, they either didn't happen within our observable volume, or they were too subtle for Planck to detect, or the collision signatures are hidden in noise. But future CMB experiments, like the upcoming Light B-RD satellite and Simon's Observatory, will have better sensitivity and might find what Planck missed. But the CMB isn't the only place to look. Another possibility is gravitational waves. When two bubble universes collide, the collision produces gravitational radiation ripples in spacetime itself. These gravitational waves would propagate through the universe, carrying information about the collision. If we could detect them, we could learn about the properties of the other bubble, including potentially its vacuum energy and the value of its cosmic speed limit. The challenge is that gravitational waves from bubble collisions would have very long wavelengths, far longer than the waves detected by LIGO and Virgo from black hole mergers. We're talking about wavelengths comparable to the size of the observable universe. Detecting such waves requires different techniques, like pulsar timing arrays or space-based interferometers. The upcoming Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, might be sensitive to some of these ultra-long wavelength gravitational waves, though detecting bubble collision signals would require extraordinary luck and even more advanced instruments in the future. Now, here's where things get really speculative but fascinating. What about communication across the multiverse? If other universes exist, could we send signals to them? Or receive signals from them? This sounds like pure science fiction, but some physicists have seriously explored the idea. One possibility involves wormholes tunnels through space-time connecting different regions. In general relativity, wormholes are mathematically possible, though they'd require exotic matter with negative energy density to keep them open. If wormholes could connect different bubble universes, they might allow information to pass between them. Physicist Kip Thorne, who won the Nobel Prize in 2017 for his work on gravitational waves, and who consulted on the movie Interstellar, has written extensively about wormhole physics. While traversable wormholes almost certainly don't exist naturally, Thorne and others have explored whether advanced civilizations might construct them artificially. But here's an even weirder idea. What if quantum entanglement connects different branches of the many worlds multiverse? Entanglement is a quantum phenomenon where two particles share a connection such that measuring one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance, and it's been experimentally verified countless times. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their experimental work demonstrating quantum entanglement. Now, in the many worlds interpretation, when a quantum measurement happens, the universe branches. You go into one branch, seeing one outcome. Another version of you goes into another branch, seeing a different outcome. The two branches are entangled. They share quantum correlations. But they've decarred, so they can't directly communicate. Or can they? Some physicists have speculated about post-selection experiments where you might detect correlations across branches. The idea is that certain very specific quantum experiments might reveal statistical patterns that only make sense if information is leaking between branches. This is highly controversial and probably wrong, but it illustrates how seriously some researchers take the many worlds interpretation. If it's correct, then there are other versions of you in other branches, living in the same universe with the same physics, but experiencing different outcomes. You can't talk to them, but you're quantum mechanically connected to them. Let me give you another concrete example of how we might probe the multiverse by looking for variations in the fundamental constants across space. If different regions of our universe formed from slightly different vacuum states, or if we're near the boundary of a bubble universe where the physics transitions, we might see the constants slowly changing as we look in different directions or at different distances. Astronomer John Webb and his colleagues have been searching for this for decades. They use distant quasars as cosmic lighthouses. Light from these quasars passes through clouds of gas between the quasars and Earth, and the gas absorbs light at specific wavelengths determined by atomic physics. If the fine structure constant alpha were different in those clouds, the absorption wavelengths would shift slightly. By measuring these shifts, Webb can test whether alpha has changed over cosmic time or varies across space. In 1999, Webb's team published controversial results suggesting alpha might have been slightly smaller in the distant past. Subsequent observations have been ambiguous. Some datasets suggest variation, others don't. As of my last knowledge update in January 2025, the situation remains unresolved, with some tantalizing hints but no definitive evidence. If real, such variations could indicate we're in a universe that's not completely uniform, perhaps near a boundary between different vacuum states where C and other constants are transitioning. But here's what I really want you to understand. The fact that we're even having these conversations, designing these experiments, analyzing this data, that's revolutionary. 50 years ago, the multiverse was pure philosophy, untouchable by science. Today, we're actively searching for evidence. We're designing instruments specifically to detect signatures of other universes. We're taking the idea seriously enough to invest billions of dollars in telescopes and satellites that might find proof. And here's the profound thing. Even if we never find definitive evidence, the search itself is transforming our understanding of what's possible. We're learning that the multiverse hypothesis makes predictions. It's not unfalsifiable nonsense. We're learning how to test ideas that seem untestable. We're pushing the boundaries of empirical science to encompass questions about the structure of reality itself. Think about what this means for you, personally. You're alive at a moment in history when humans are genuinely trying to answer whether other universes exist. Your ancestors couldn't even conceive of this question. Your descendants might know the answer. But you're in the middle, in the uncertainty, in the exploration. That's a privilege. Now, let me address a concern you might have. What if we're wrong? What if all of this eternal inflation, string theory, many worlds, the landscape, what if it's all just elaborate mathematical fantasy with no connection to reality? That's a fair worry. Science has been wrong before. Confident theories have collapsed. The multiverse might go the same way. But here's the thing. Even if the specific models are wrong, the question remains. Why does the speed of light have the value it does? Why are the constants of nature fine-tuned for complexity? These aren't questions that disappear if the multiverse turns out to be fiction. They're questions that demand answers, and the multiverse is currently our best attempt at answering them. If it's wrong, we need something better, not a retreat into "it just is that way." And here's what's beautiful. Physics has a way of surprising us. Theories that seemed wild and speculative sometimes turn out to be right. Continental drift was ridiculed until plate tectonics explained it. The Big Bang was considered absurd until the CMB confirmed it. Quantum mechanics sounded like magic until experiments proved it. The multiverse might be next, or it might not. But the only way to find out is to keep looking, keep calculating, keep observing. In the next section, we're going to take a different approach. We're going to explore what life would actually be like in universes with different speeds of light. We're going to use physics to construct thought experiments. What would stars look like if c were twice as fast? What would atoms be like if c were half as slow? Could life exist in those universes? And if so, what would it be like? This is where the abstract becomes concrete, where the mathematics becomes experiential. We're going to imagine what it's like to live in a universe radically different from ours. And then, we're going to ask a question that should haunt you. If intelligent life arose in one of those other universes, would they be asking the same questions we are? Would they be wondering if there are other universes where the speed of light is different? Would they be searching for us the same way we're searching for them? The journey continues. Stay with me. Let's do something different now. Let's stop talking about the multiverse in the abstract and actually visit some of these other universes. Not literally, of course, we can't travel to other bubble universes. But we can use physics to simulate them, to calculate what they'd be like. We can explore the landscape of possibilities and see what happens when you turn the dials, when you change the speed of light, and watch how reality transforms. So imagine you have a control panel in front of you. There's a dial labeled C, Cosmic Speed Limit, currently set to 299,792,458 meters per second. You reach out and start turning it. What happens? First, let's turn it up. Let's make C faster, say, twice as fast as in our universe, about 600 million meters per second. What changes? Well, immediately, the fine structure constant alpha, which determines the strength of electromagnetic interactions, drops by half. Alpha is proportional to 1c, so making c bigger makes alpha smaller. Electromagnetic forces get weaker. Electrons orbit atomic nuclei more loosely. Atoms become larger and more diffuse. Think about what this means for chemistry. Chemical bonds depend on electromagnetic interactions between electrons in different atoms. Weaker electromagnetic forces mean weaker bonds. Molecules are less stable, easier to break apart. Complex molecules like proteins and DNA might not be stable at room temperature. They'd vibrate and twist and fall apart. But it gets worse. Stars depend on a delicate balance between gravity, which wants to crush them, and radiation pressure, which wants to blow them apart. Radiation pressure comes from photons produced by nuclear fusion in the star's core. If C is larger, photons carry more momentum. Momentum is energy divided by speed. And while photons carry more energy in this universe, the relationship changes such that radiation pressure is weaker relative to gravity. Wait, let me recalculate that. Actually, photon momentum is EC, so if C increases, momentum decreases for a given energy. That means radiation pressure is weaker. Stars would be more dominated by gravity. They'd compress more, get hotter, burn faster. A star like our sun would exhaust its fuel in millions of years instead of billions. Planets wouldn't have time to cool down. Oceans wouldn't have time to form. Life wouldn't have time to evolve beyond maybe simple chemistry. This is what I mean by fine-tuning. You can't just change one constant and expect everything else to work. The universe is an integrated system. Change C, and you change everything: atomic physics, chemistry, stellar evolution, cosmology. And most changes are fatal to complexity. But let's keep turning the dial up. Make C 10 times faster, 3 billion meters per second. Now we're in a really strange universe. Electromagnetic forces are so weak that atoms barely hold together. You might not have stable atoms at all, at least not the way we know them. Electrons might not be bound to nuclei in well-defined orbitals. Matter might exist in some exotic plasma state, even at low temperatures. Stars? Forget about it. With such weak electromagnetic forces, you might not even get nuclear fusion working properly. The electromagnetic repulsion between protons that needs to be overcome for fusion might be weaker, but the quantum tunneling probabilities change. The stellar structures change. You'd probably get very different stellar dynamics if you get stars at all. This universe is likely sterile. No atoms, no chemistry, no stars, no planets, no life. Just a dark, cold expanse of elementary particles that never coalesce into anything interesting. Now let's go the other way. Turn the dial down. Make C slower half its value in our universe, about 150 million meters per second. Now alpha doubles. Electromagnetic forces get stronger. Electrons orbit nuclei more tightly. Atoms shrink. This sounds less immediately catastrophic, right? Smaller atoms, tighter bonding, stronger chemistry. Maybe this universe is even better for life? Not so fast. Stronger electromagnetic forces mean higher energy scales for atomic transitions. Atoms emit and absorb higher energy photons. The visible spectrum shifts. More importantly, the balance between different forces changes. The strong nuclear force, which holds protons and neutrons together in atomic nuclei, doesn't depend on C in the same way. So the ratio between electromagnetic and strong forces changes. This affects nuclear physics. The stability of different atomic nuclei depends on the balance between the strong force holding nucleons together and the electromagnetic force pushing protons apart. Change that balance, and you change which nuclei are stable. Carbon, oxygen, nitrogen, the elements of life might not be stable. You might get a universe where only helium and a few light elements are stable, with all heavier elements decaying quickly. And stars would be affected too. With stronger electromagnetic forces, radiation pressure in stars would be stronger. Stars would be puffier, cooler, they'd burn slower. That might sound good longer stellar lifetimes, more time for life to evolve. But cooler stars emit less high-energy radiation. Planets around such stars would need to be closer to stay warm. And closer planets face tidal locking, with one side always facing the star, making habitable zones much more restricted. Plus, stellar nucleosynthesis, the production of heavy elements in stars, depends on specific nuclear reactions with specific energy barriers. Change the electromagnetic force, and you change these barriers. The stellar processes that create carbon, oxygen, and iron might not work. You might get a universe with long-lived stars that only produce hydrogen and helium. Again, no chemistry, no life. Keep turning the dial down. Make C 1/10 its value in our universe, 30 million meters per second. Now alpha is 10 times larger. This universe is radically different. Electromagnetic forces dominate everything. Atoms, if they exist, are tiny and superdense. Electrons move at substantial fractions of the speed of light, even in their ground states, making relativistic effects important in basic chemistry. The quantum field theory of electromagnetism might behave differently, with strong quantum corrections and potential new phenomena. You'd probably have a universe where electromagnetic interactions are so strong that matter can't exist in familiar forms. Particles might immediately annihilate or form strange condensates. The vacuum itself might be unstable to electromagnetic phenomena. This universe likely doesn't last long or produces nothing but extreme high-energy physics with no stable structures. Are you seeing the pattern? Turn C too high, and electromagnetic forces are too weak to hold atoms together. Turn C too low, and electromagnetic forces are so strong they dominate everything else, destabilizing matter. There's a narrow window, and we're in it where C has a value that allows for rich, complex chemistry and stable stellar evolution. But let's get even more specific. Let me introduce you to a physicist named Max Tegmark, who's at MIT and has done extensive work on the habitable range of fundamental constants. In a famous 2006 paper, Tegmark and colleagues calculated the range of possible values for various constants that would still allow for observers. Not necessarily human-like observers, but any kind of complex information processing systems. For the fine structure constant alpha, which depends on C, Tegmark found that alpha could vary by maybe a factor of 2 or 3 in either direction before you lose the possibility of complex chemistry. Given that alpha is currently about 1/137th, this means C could range from maybe half to twice its current value, a factor of 4 total range, before the universe becomes too inhospitable for any imaginable form of life. That's a narrow window. The landscape has potentially 10 to the 500 different vacuum states. If C can vary over many orders of magnitude across this landscape, then only a tiny fraction, maybe 1 in a trillion allows for observers. And yet we find ourselves in that tiny fraction. Why? Because the vast majority of the landscape is empty. Nobody's there to wonder about it. This is the anthropic principle in action, and it's not just hand-waving, it's quantitative. We can calculate the habitable range, compare it to the range of possibilities, and confirm that yes, we're in a special place, and yes, the anthropic explanation is the best we have. But let's push further. Let's imagine a universe where C is exactly the same as ours, but where other constants have changed in coordinated ways. What if C is the same, but the mass of electrons is different? Or the strength of the strong nuclear force? You could have a universe with our value of C, but radically different physics. For instance, imagine a universe where C is unchanged, but the electron mass is much larger, say, 10 times heavier. Heavier electrons would orbit nuclei more tightly, atoms would be smaller, quantum effects would be less pronounced. Chemistry would still work, but it would be different. Reaction rates would change, bonding energies would change. You might have a universe where silicon-based life is more favorable than carbon-based life, because the increased atomic masses change which elements are most versatile. Or imagine a universe where C is the same, but the strong nuclear force is slightly weaker. You'd have fewer stable nuclei, maybe no elements heavier than carbon or stable. That's a universe where chemistry is impoverished, where you have hydrogen, helium, lithium, beryllium, boron, carbon, and that's it. Could life evolve with such limited chemistry? Maybe, if it's very different from our life. Maybe simple self-replicating molecules could form from just light elements. But it would be incredibly constrained. The point is, C is just one constant among many, and they all have to work together. The multiverse, if it exists, isn't just a collection of universes with different light speeds. It's a vast space of possibilities where all constants vary, and the combinations that allow for complexity are rare intersections of multiple constraints. Think of it like a combination lock with 100 dials. Each dial represents a different constant C, electron mass, strength of gravity, strength of the strong force, and so on. For the lock to open, for observers to exist, all the dials have to be in very specific ranges simultaneously. The number of possible combinations is astronomical, but only a tiny fraction opens the lock. We find ourselves staring at an open lock because closed locks have nobody inside to observe them. Now let me blow your mind one more time. What if C isn't just different in other universes, but actually changes with time within a universe? What if the cosmic speed limit was different in the early universe and is slowly changing even now? This idea is called a varying speed of light cosmology, and it's been seriously explored by physicists including Joe Maguire and John Barrow in the late 1990s and early 2000s. The idea is that in the very early universe, during the first instance after the Big Bang, 100 might have been much larger than it is now, allowing distant regions to communicate and establish thermal equilibrium. As the universe evolved, C decreased to its current value. This sounds crazy. Isn't C supposed to be constant? Well, locally, yes. Special relativity requires that C is constant for any local observer. But general relativity allows for spacetime itself to have different properties at different times or places. If the vacuum energy is changing as the universe evolves, then the stiffness of spacetime changes, and so does the cosmic speed limit. Varying speed of light cosmologies, were originally proposed as alternatives to inflation ways to solve the horizon problem without invoking exponential expansion. They haven't been as successful as inflation at explaining observations, and most physicists don't think c actually varies with time. But the fact that the idea is even coherent, that general relativity and quantum field theory allow for it, is remarkable. It shows that c, despite being called a constant, is actually a dynamical property of spacetime that could, in principle, change. Imagine living in a universe where c is decreasing over time. When the universe was young, light moved faster. Causality worked differently. Distant events could influence each other more quickly. As you move forward in time, c slows down. Information propagates more slowly. The universe becomes more viscous, more sluggish. If intelligent beings evolved in such a universe, they'd measure c at different points in their history and find it changing. They'd know directly that the cosmic speed limit isn't fundamental, but emergent from something deeper. Now imagine you're one of those beings, living in a universe where c has been decreasing for billions of years. You look back at ancient light from distant galaxies and see evidence that c was different in the past. You wonder, will c keep decreasing? Will it reach zero? What happens then? Does causality break down? Does the universe freeze? These are the kinds of questions that beings in other universes might be asking. And here's what's profound. We're asking similar questions about our universe. We wonder about the cosmological constant, about dark energy, about whether the laws of physics might evolve. We're not so different from hypothetical observers in universes with different physics. We're all trying to understand the cosmos we find ourselves in, using the tools we have. And that brings me to a realization that I want you to sit with. The speed of light, the fundamental constants, the laws of physics, they're not arbitrary. They're not meaningless. They determine what's possible, what can exist, what experiences can be had. Change them, and you change the space of possibilities. The multiverse, if it exists, isn't just a collection of dead universes. It's a vast space of possibility, where different configurations allow for different kinds of structure, different kinds of complexity, maybe even different kinds of consciousness. In the next section, we're going to explore that last idea, consciousness and observers in the multiverse. We're going to ask, if other universes have different physics, could they have different kinds of minds? Could there be observers who experience time differently, who process information differently, who have forms of consciousness we can't even imagine? And we're going to confront a question that should fundamentally change how you see yourself. What does it mean to be an observer in a universe with this specific speed of light, these specific laws? How does the physics of our universe shape not just our bodies, but our minds, our perceptions, our very experience of existence? This is where physics meets philosophy, where cosmology meets consciousness, and where everything we've discussed becomes deeply personal. So let's talk about you. Not the abstract observers that physicists invoke when discussing the anthropic principle, but you specifically, the person watching this video right now. You exist because the speed of light in our universe is 299,792,458 meters per second. Not approximately that value, exactly that value, at least within our ability to measure it. And that value, combined with all the other constants we've discussed, determines everything about your physical existence. Your body is made of atoms held together by electromagnetic forces whose strength depends on C. Your neurons fire using electrochemical signals that propagate at speeds determined by the physics of ion channels and membrane potentials physics that ultimately derives from C. Your thoughts, your memories, your sense of self, all of these emerge from neural activity patterns that unfold according to the laws of physics in a universe with this particular cosmic speed limit. But here's what's really strange. Your perception of time itself is shaped by C. This is going to sound abstract, but bear with me because it's profound. The speed of causality, what we call C, determines the rate at which information can propagate through space. That rate sets a fundamental limit on how quickly events can influence each other, how quickly causes can produce effects. And consciousness, whatever it is a process of information integration, of causal influences flowing through neural networks. Think about what this means. In a universe where c is much faster, where information can propagate more quickly, would consciousness unfold faster? Would subjective experience feel accelerated? Or would it feel the same, because all the physical processes, neural firing, chemical reactions, everything would speed up together, leaving the subjective experience unchanged? This is called the problem of consciousness scaling, and it gets to something deep. We don't know whether subjective experience, the felt quality of being conscious, is tied to absolute physical timescales or relative timescales. If you could speed up all the physical processes in a brain by a factor of 10, would that brain experience time passing 10 times faster? Or would each subjective moment take 10 times longer to process, leaving the experience of time's flow unchanged? Physicists and philosophers have argued about this for decades. There's no consensus. But here's what we do know. The speed of light sets an absolute scale to causality in the universe. It's not arbitrary in the sense that all observers agree on its value within a given universe. So if consciousness depends on causal processes, and causal processes are limited by c, then c might set an absolute scale for consciousness itself. Let me give you a concrete example. Imagine a brain made of neurons that communicate using light signals instead of electrochemical signals. Optical neurons, if you will, something that might exist in a universe with very different chemistry. These neurons would communicate at the speed of light, much faster than biological neurons, which transmit signals at roughly 100 meters per second. Would a brain made of optical neurons think faster than a biological brain? Would it experience more subjective time in a given objective duration? The answer depends on what consciousness actually is. If consciousness is just information processing, and faster processing means more computation per unit time, then yes, an optical brain would think faster, experience more, live a richer subjective life in the same objective time frame. But if consciousness requires not just processing but integration, where different parts of the brain need to communicate and synchronize, then maybe the speed limit of c becomes a bottleneck. An optical brain might process faster locally, but it still can't communicate across its volume faster than light speed allows. Now scale this up to the cosmic level. In a universe where c is much larger, where causal influences propagate faster, could civilizations develop more quickly? Could intelligence arise and evolve through more iterations in the same cosmic time? Would a billion years in a high C universe correspond to trillions of years of subjective experience and evolutionary development? Or would everything scale together, stars burning faster, evolution happening faster, thoughts happening faster, leaving the subjective experience identical? We don't know. And this uncertainty points to a deep mystery about consciousness and its relationship to physics. But let me tell you about someone who's thought deeply about these questions. Physicist and computer scientist Max Tegmark, who I mentioned earlier. Tegmark has proposed what he calls the mathematical universe hypothesis, the idea that reality is fundamentally mathematical, and that consciousness is a particular kind of information pattern that can emerge in systems with sufficient complexity and integration. In Tegmark's view, the specific values of constants like c determine which mathematical structures can be realized in a universe, which patterns of information processing can exist. Change c, and you change the space of possible conscious experiences. In universes with very different c, consciousness might be impossible. The physics might not support the kind of complex, integrated information processing that gives rise to subjective experience. In other universes, consciousness might be possible, but radically different based on different substrates, different timescales, different organizational principles. Think about what this means for the multiverse. If consciousness is possible in multiple universes with different values of C, then the multiverse contains not just different physical structures, but different phenomenologies, different ways of experiencing existence. There might be universes where conscious beings experience time much faster than we do, where a single second of our time feels like hours or years to them. There might be universes where consciousness is much slower, where beings take centuries to complete a single thought. And here's the really mind-bending part. From the inside, from the subjective perspective, each of these beings would feel like their experience is normal. They wouldn't know they're thinking fast or slow unless they could compare themselves to beings in other universes. Just like you don't feel like you're thinking at any particular speed, you just think. And that feels like the normal rate of thought. This is called the problem of subjective scales, and it highlights something crucial. Your experience of reality is shaped not just by what exists, but by the rates and scales at which processes unfold. And those rates and scales are determined by the fundamental constants, including C. Let me make this even more personal. The fact that you're experiencing this moment right now, reading these words, having thoughts about the multiverse, and the speed of light, all of this is only possible because C has the value it does. If C were significantly different, the atoms in your body might not be stable. The chemistry of life might not work. Stars might not produce the heavy elements you're made of. You literally wouldn't exist. But it's more subtle than that. Even small changes in C might allow for life, but different kinds of life, with different neural architectures, different information processing speeds, different sensory modalities. Beings in a universe with C, just 10% larger or smaller, might perceive reality in fundamentally different ways. Their color vision might span different wavelengths. Their sense of time might be compressed or dilated. Their thoughts might follow different patterns. You are shaped by the physics of this universe in ways you can't even perceive because you have no reference point. You can't step outside your own consciousness and see how it would differ in a universe with different laws. But you can think about it, and in thinking about it, you can appreciate something profound. You are not separate from the cosmos. You are a particular pattern of matter and energy, organized in a particular way that emerges in a universe with particular laws. Change the laws, and you change the pattern. You are the universe experiencing itself, but specifically, you are this universe experiencing itself. Now let me introduce you to another key thinker, philosopher and cognitive scientist Daniel Dennett, who passed away in 2024. Dennett spent his career arguing that consciousness is not some mysterious, irreducible essence, but a physical process, an emergent property of complex information processing. In Dennett's view, understanding consciousness means understanding the functional architecture of the brain, the algorithms it runs, the information it processes. If Dennett is right, then consciousness is substrate independent. It's not about what you're made of, but about what you do with information. And if that's true, then in principle, any universe that allows for complex information processing could give rise to consciousness. The specific value of C doesn't matter in absolute terms. What matters is whether the physics allows for the emergence of integrated, self-referential information systems. But here's the catch. Not all values of C allow for that. As we've seen, if C is too different from its actual value, atoms might not be stable, chemistry might not work, stars might not form. Without stable matter and energy flows, you can't have complex information processing. So C does matter not because consciousness requires some specific value of C, but because C determines whether the preconditions for consciousness can exist. This is a crucial distinction. The multiverse might contain many universes with different values of C, but only a small fraction of them support the physics necessary for consciousness to arise. And we find ourselves in one of those rare universes, not because we're special, but because the universes without consciousness have nobody in them to wonder about it. But here's a question that should haunt you. Are we typical? Among all the observer-supporting universes in the multiverse, is our universe a typical example? Or are we in some kind of special, unusual universe? This question is called the typicality problem in multiverse cosmology, and it's surprisingly hard to answer. If the multiverse is infinite, with infinitely many observer-supporting universes, then there's no well-defined notion of typical. You need to specify a measure, a way of counting and comparing universes. Different measures can give different answers. For instance, if you count by volume how much space each universe contains, then universes with longer inflation periods, which produce more space, count more. But if you count by observers how many conscious beings exist in each universe, then universes with longer stellar lifetimes and more habitable planets count more. These two measures can favor different values of the constants, including c. Some physicists, including Andre Linde and Vitali Van Churen, have argued that we should count by observers, not by volume, a measure called causal patch cosmology. In this approach, you ask, among all the observers who will ever exist in the multiverse, what fraction experience a universe with constants similar to ours? The answer depends on detailed calculations about star formation, planet formation, the emergence of life, and the duration of habitable conditions. As of my knowledge cutoff in January 2025, these calculations are still preliminary and controversial. Different assumptions give different results. But the mere fact that we can ask these questions quantitatively, that we can calculate the distribution of observers across the multiverse, and compare predictions to what we observe is remarkable. This is science, not philosophy. And here's what some of these calculations suggest. We might be living in a fairly typical observer-supporting universe. The values of our constants, including c, seem to fall within the range that maximizes the number of observers given certain plausible assumptions. That's not proof of the multiverse, but it's consistent with the anthropic explanation. If our constants were weirdly special, even within the observer-supporting range, that would be harder to explain. But let me bring this back to you personally, because I don't want this to feel like abstract philosophy. You are an observer in this universe right now. The fact that you exist, that you're capable of thinking about these questions, is a consequence of the physics we've been discussing. The speed of light, the fundamental constants, the initial conditions of the Big Bang, all of this had to be just right for you to be here. And here's what I find beautiful about that. You're not an accident, but you're also not inevitable. You're contingent. You exist because of a specific chain of causes stretching back to the origin of the universe, a chain that could have been different but wasn't. In other universes, that chain is different, and beings like you don't exist. But other beings might, experiencing reality in their own ways, shaped by their own physics. The multiverse, if it exists, is not just a collection of sterile mathematical structures. It's a vast space of possible experiences, possible consciousnesses, possible ways of being. And you're one instantiation of that. One particular way the cosmos has organized itself to become aware of its own existence. Does that make you feel small and insignificant? Or does it make you feel connected to something larger? I'd argue both simultaneously. You're cosmically insignificant in the sense that the multiverse is vast beyond comprehension, and your existence is a tiny fleeting pattern in an infinite expanse. But you're also cosmically significant in the sense that you are the universe experiencing itself, a part of the whole that has become aware of the whole. In fact, let me propose something radical. Maybe the question, do other universes have different light speeds, is actually asking, are there other ways to exist? And the answer is probably yes. The multiverse, if real, contains other ways to be, other physical laws, other constants, other forms of structure and complexity. Some of those ways probably support consciousness. Most don't. But the ones that do contain beings asking similar questions, wondering about the nature of reality, trying to understand their place in the cosmos. And here's the final twist. those beings might be searching for us, the same way we're searching for them. Not through radio signals, we can't communicate across the multiverse, but through understanding, by working out the mathematics of possible universes, by calculating which constants allow for observers, by exploring the landscape of possibilities. They're constructing a map of the multiverse. And somewhere on that map, they might find our universe with our value of C, and they might realize there could be observers there too, asking the same questions we're asking. In a sense, we're already in contact with them, not through signals, but through shared understanding. If mathematics is universal, if logic is universal, then any intelligent beings anywhere in the multiverse will discover the same mathematical structures, the same logical principles. They'll work out quantum mechanics and general relativity, even though their universe might have different constants. They'll discover that the landscape of possible universes is vast and mostly sterile, and they'll realize they're in one of the rare, precious universes that supports complexity. That shared understanding, that shared realization, is a kind of connection. We're linked to other observers across the multiverse, not by causal chains, but by the structure of reality itself, by the mathematics that underlies all possible universes. In the next section, we're going to zoom out even further. We're going to ask, why does mathematics work? Why does the universe follow mathematical laws at all? And we're going to explore the most radical possibility of all, that reality is mathematics, that the multiverse is the set of all mathematically consistent structures, and that the speed of light in our universe is just one number and one structure among infinitely many. This is where we reach the deepest level, where physics meets metaphysics, where science meets the ultimate questions about existence. Stay with me. We're almost at the end, and the revelations are going to be profound. We've talked about different universes with different values of C. We've talked about eternal inflation, string theory, quantum cosmology, consciousness, and observers. But now I want to ask you a question that goes deeper than all of that. Why is there something rather than nothing? Why does any universe exist at all, whether it has our speed of light or a different one? This is the ultimate question, the one that physics can't answer by itself, because physics assumes existence. It studies what exists, how it behaves, how it evolves. But it doesn't explain why anything exists in the first place. That seems like a question for philosophy or religion, not science. But what if I told you there's a scientific approach to this question? What if the answer to why does anything exist is connected to the answer to why does the speed of light have the value it does? What if both questions have the same answer, and that answer is stranger than you can imagine? Let me introduce you to an idea called the mathematical universe hypothesis, most clearly articulated by Max Tegmark in his 2008 paper, The Mathematical Universe, and his 2014 book, Our Mathematical Universe. Tegmark's central claim is this: physical existence equals mathematical existence. If a mathematical structure is logically consistent, it exists physically, not as an abstract idea in some Platonic realm, but as a concrete, physical reality. In other words, the multiverse isn't just a collection of different inflating regions or quantum branches. The ultimate multiverse is the set of all mathematical structures. Every possible universe that can be described mathematically, every set of consistent laws, every configuration of fields and particles, every value of every constant exists with the same ontological status as our universe. Think about what this means. There's no fundamental difference between our universe and a mathematical structure. Our universe is a mathematical structure. Specifically, it's a structure that includes 3 spatial dimensions: one time dimension, quantum fields with particular properties, and constants like C with particular values. But it's just one structure among infinitely many. This sounds insane at first. How can mathematics abstract, intangible be the same as physical reality, concrete, tangible? But Tegmark argues we've been thinking about this backwards. We think of mathematics as a human invention, a language we use to describe physical reality. But maybe mathematics isn't describing reality. Maybe mathematics is reality. The physical properties we perceive, hardness, color, warmth, are just how certain mathematical patterns feel from the inside, experienced by subsystems of those patterns, like us, that have evolved to process information and survive. Let me give you an analogy. Imagine you're a character in a video game. From your perspective, the game world is physical. You see landscapes, feel collisions, experience time passing. But from outside, the game is just mathematical rules algorithms that specify how objects move, how forces work, how pixels are colored. The physics of the game world is just mathematics running on a computer. And you, the character, are also mathematics, a pattern of data representing your state, updated according to rules. Now, here's the key. Do you need the computer? If the mathematical rules fully specify what happens, does it matter whether they're being run on hardware? Or does the mathematical structure exist independently, with its own internal consistency, and the hardware is just one way of representing it? Tegmark argues the hardware is unnecessary. Mathematical structures exist in themselves, with their own internal logic and consistency. A video game world exists mathematically, whether or not anyone builds a computer to run it. And similarly, our universe exists mathematically, whether or not there's some external reality implementing it. This is a profound ontological claim. Existence is mathematical consistency. If a structure is mathematically well-defined and logically consistent, it exists. Period. There's no need for anything to create it, to implement it, to make it real. Its mathematical existence is its physical existence. And if this is true, if the mathematical universe hypothesis is correct, then the multiverse contains every possible mathematical structure. Every value of C that's consistent with some mathematical physics exists in some universe. In fact, every possible physics exists. Universes with different numbers of spatial dimensions, different force laws, different particle types, even different logical structures, all exist with equal ontological status. Our universe, with its specific value of C, is just one mathematical structure among infinitely many. We find ourselves in this one because it's one of the rare structures complex enough to support observers. The vast majority of mathematical structures are too simple or too chaotic to produce consciousness. But the ones that do contain beings who wonder why their universe has the properties it does. Now, you might object. This doesn't answer the question, why is there something rather than nothing? It just replaces, why does our physical universe exist? With why do mathematical structures exist? Have we really made progress? Tegmark's answer is yes, because mathematical structures don't need to be created or caused. They exist necessarily as a matter of logic. The number 3 doesn't need to be created. It exists by definition as part of the mathematical structure of arithmetic. Similarly, a mathematical structure describing a universe doesn't need to be created. It exists by virtue of being mathematically consistent. Think of it like this. Asking, why do mathematical structures exist? Is like asking, why is 2 2 equals 4? The answer is, because that's what those symbols mean. It's not a contingent fact that could be otherwise. It's a logical necessity. And if physical existence equals mathematical existence, then the existence of universes is also a logical necessity. They exist because they're mathematically possible. This eliminates the need for a creator, for a first cause, for any external explanation of existence. Universes don't need to be created. They exist by virtue of being consistent mathematical possibilities. And the question, why this universe, gets answered by the anthropic principle, because this universe is one of the rare consistent possibilities that support observers. But here's where it gets really wild. If the mathematical universe hypothesis is correct, then not only do all possible universes exist, but all possible levels of existence exist. Tegmark distinguishes 4 levels of multiverse. Level 1. Different regions of space beyond our cosmic horizon, within our universe. These regions have the same laws, but different initial conditions. Level 2. Different bubble universes in eternal inflation, with potentially different constants, but the same general framework of laws. Quantum field theory, general relativity. Level 3. Different branches of quantum mechanics in the many worlds interpretation, all sharing the same Hamiltonian. Level 4. Different mathematical structures entirely, with different laws, different numbers of dimensions, different logical foundations. We've been mostly discussing level 2 bubble universes with different values of C, but the mathematical universe hypothesis encompasses all 4 levels. Level 4 is the ultimate multiverse, containing every possible way reality could be structured. And here's what this means for the speed of light. C isn't just different in different level 2 bubble universes. In level 4, there are mathematical structures where the concept of C doesn't even exist, universes where space-time doesn't exist, where causality works differently, where the whole framework of physics is alien to our understanding. Imagine a mathematical structure with 5 spatial dimensions and 2 time dimensions. How would causality work there? Would there be a cosmic speed limit at all? Or imagine a discrete universe where space and time come in chunks, like pixels, rather than being continuous. How would speed be defined? Or imagine in a causal universe where events don't have causes in the normal sense, a universe of pure mathematical pattern without any notion of temporal flow. These aren't just thought experiments. If the mathematical universe hypothesis is correct, these are actual, existing realities with the same ontological status as our universe. And some of them might support forms of complexity, information processing, even consciousness, but based on completely different principles than the physics we know. Think about what this means for observers in those universes. They'd have no concept of the speed of light, because their mathematics doesn't include anything analogous to it. But they might have their own fundamental constants, their own anthropic questions. They might wonder why their version of reality has the structure it does, and they might develop their own version of the multiverse hypothesis to explain it. And here's the profound thing. From a level 4 perspective, all of these universes, including ours, are on equal footing. None is more real than any other. Our universe, with C equals 299,792,458 meters per second, isn't special except that it's the one we happen to inhabit. It's one mathematical structure among infinitely many, one way reality can be organized, one pattern in the infinite space of possibilities. Does this make you feel insignificant? Or does it make you feel amazed? I find it both humbling and exhilarating. Humbling because our universe, everything we've ever known, experienced, or imagined, is just one tiny corner of mathematical reality. But exhilarating because we're capable of grasping this, of understanding our place in the vast scheme of things. We're one small pattern in an infinite multiverse, but we're a pattern capable of comprehending the whole. Now, let me address the obvious objection. The mathematical universe hypothesis is unfalsifiable, right? If every possible universe exists mathematically, we can't test whether that's true. We can only observe our universe. So isn't this just metaphysics dressed up as science? Tegmark argues no, for several reasons. First, the hypothesis makes predictions. If all mathematical structures exist, then we should find ourselves in a structure that's typical of observer-supporting structures. We can calculate what's typical and compare it to observations. If our universe is weird even within the observer-supporting subset, that would be evidence against the hypothesis. Second, the hypothesis has explanatory power. It explains why the fundamental constants have the values they do. Anthropic selection from the space of all possibilities. Why the laws of physics are mathematical, because physical laws are mathematics. And why anything exists at all, because mathematical consistency implies existence. Third, The hypothesis is parsimonious in a deep sense. It doesn't add extra entities, it actually removes them. Instead of saying physical laws exist and separately, mathematical structures exist, it says they're the same thing. That's simpler, more elegant. But here's what's really important. Whether or not the mathematical universe hypothesis is true, the exercise of thinking about it changes how you see reality. It shows you that existence might be stranger, deeper, more abstract than you thought. It suggests that the physical world you perceive solid, tangible, concrete might be, at a fundamental level, pure pattern, pure mathematics, pure information. And that brings us full circle to the speed of light. C is a number in a mathematical structure. That's all it is, a parameter in the equations describing our universe. In other mathematical structures, that parameter has different values or doesn't exist at all. And all of those structures are equally real, equally existent, differing only in their mathematical properties. You exist in this structure with this value of C because this is one of the structures complex enough to support your existence. And the fact that you can understand this, that you can grasp the concept of the multiverse, the landscape of possibilities, the mathematical nature of reality, is itself extraordinary. You are a pattern in a mathematical structure that has become aware of its own mathematical nature. You are mathematics reflecting on mathematics. In the final section, we're going to bring all of this together. We're going to step back and see the full picture: eternal inflation, quantum branching, string theory, the anthropic principle, consciousness, and mathematical existence. We're going to see how all these ideas connect into a coherent worldview. And we're going to ask, what does this mean for how you live your life? If the multiverse is real, if other universes have different speeds of light, if reality is vast beyond comprehension, how should that change how you think about yourself, your purpose, your place in the cosmos? This is where science becomes wisdom. This is where understanding transforms into meaning. Stay with me for the final section. We're going to end with something that will change how you see everything. So here we are, nearly 3 hours into this exploration, and I want to take a moment to acknowledge what we've accomplished together. We started with a simple question: do other universes have different light speeds? And we've journeyed through eternal inflation, quantum cosmology, string theory, consciousness studies, and the mathematical nature of reality itself. We've seen that the answer to our question is almost certainly yes. Other universes, if they exist, likely have different values for the cosmic speed limit we call c. We've explored how this would affect their physics, their chemistry, their capacity to support life and consciousness. And we've discovered that this question opens onto much deeper questions about existence, meaning, and our place in the cosmos. But now, I want to bring this home. I want to talk about what all of this means for you, personally, in your everyday life. Because understanding the multiverse isn't just an intellectual exercise. It's a framework for making sense of your existence, for finding meaning in a cosmos that might be far stranger and vaster than anyone imagined. Let's start with a simple observation. You are here. You exist. You are conscious, aware, capable of thinking about these questions. And as we've seen, that's an extraordinarily improbable situation. The constants of nature, including the speed of light, had to fall within a very narrow range for you to exist. The initial conditions of the universe had to be just right. Billions of years of cosmic evolution had to unfold in exactly the way they did. If you believe we live in a single universe with no deeper explanation for its properties, then your existence is a miracle, an incomprehensibly unlikely accident. The odds against you existing are so astronomical that it's almost irrational to believe you're here. But if the multiverse is real, if there are countless universes with different properties, then your existence becomes comprehensible. You're here because, in the vast space of possibilities, some universes support observers, and observers necessarily find themselves in observer-supporting universes. It's not a miracle. It's selection, Does that make your existence less special? I don't think so. In fact, I think it makes it more special in a different way. You're not special because you're unique. There are probably countless other conscious beings in other observer-supporting universes. But you're special because you're specific. You are this particular pattern of matter and energy in this particular universe, experiencing this particular moment. There might be other observers, but there's only one you. And here's what's beautiful. The multiverse doesn't diminish your significance. It contextualizes it. You exist in a specific context, a universe, with specific laws, specific constants, specific history. That context shapes everything about you. Your body, your brain, your experiences, your possibilities. Understanding that context, understanding why the speed of light is what it is, and how that enables your existence, gives you a deeper appreciation for the specificity of your situation. Think of it like this. You could have been born in a different country, a different time period, a different family. Each of those contexts would have shaped you differently. You'd still be you in some sense, but a very different version of you. Now extend that. You could have existed in a universe with slightly different constants. You'd be made of different atoms, have different chemistry, experience reality differently. And the fact that you exist in this particular context, this universe, this timeline, this body, is not inevitable. It's contingent, specific, and in a sense, miraculous. But let me push further. If the multiverse is real, then in some sense, you do exist in other contexts. Not literally you. The specific pattern of memories and experiences that constitutes your identity is unique to this universe, this timeline. But other beings, similar to you in some ways, different in others, exist in other universes. Versions of humanity might have evolved in universes with slightly different constants. Totally alien forms of consciousness might exist in universes with radically different physics. And all of those beings, all of those consciousnesses, all of those experiences, they're all part of the multiverse. The totality of existence includes not just our universe, but all possible universes, all possible forms of structure and complexity, all possible ways of being conscious. From this perspective, you're not alone in existence. You're part of a vast community of conscious beings spread across the multiverse, experiencing reality in myriad ways, each shaped by the physics of their particular universe. You can't communicate with them, can't directly interact with them, but you're connected to them by the fact that you're all manifestations of the same underlying reality mathematical structures, organized in ways that support self-awareness. Does this change how you should live your life? I think it does, in subtle but important ways. Let me suggest a few. First, it should make you appreciate the specificity of your existence. You're not just a conscious being. You're a conscious being in a universe where the speed of light is 299,792,458 meters per second, where atoms have the specific properties they do, where stars shine for billions of years, where water is liquid at room temperature. All of these specific facts enable your specific form of existence. Take a moment to marvel at that specificity, that fine-tuning, that cosmic lottery win that is your existence. Second, it should make you curious about the universe you inhabit. If you're lucky enough to exist in one of the rare universes that support complexity and consciousness, shouldn't you try to understand that universe as deeply as possible? The speed of light isn't just an abstract constant. It's part of the structure that makes you possible. Learning about physics, cosmology, the fundamental laws of nature, this is learning about yourself, about your origins, about the context that enables your existence. Third, it should make you humble. You are one small pattern in one small region of one universe among countless others. Your problems, your achievements, your entire life story, it's cosmically insignificant, but that's okay. Cosmic significance isn't the only kind of significance. Your life matters to you, matters to the people around you, matters in the local context of human society and history. You don't need to matter to the multiverse to matter. Fourth, and this might seem contradictory, it should make you feel connected to something larger. You are part of the cosmos, not separate from it, observing it from outside, but part of its structure, part of its unfolding. The atoms in your body were forged in stars. The thoughts in your mind emerge from physical processes governed by the laws of nature. You are the universe experiencing itself. One way the cosmos has organized itself to become self-aware. That's a profound connection, a kind of cosmic belonging. And finally, it should make you grateful. If the multiverse is real, most of it is sterile, empty, boring. Most possible universes don't support complexity, don't produce stars or planets, or life or consciousness. You exist in one of the rare exceptions, one of the special places where interesting things happen. That's not something you earned or deserved. It's just luck, anthropic selection. But it's still extraordinary. You won the cosmic lottery. The fact that you're here to experience anything at all is a gift. Now, I know some of you might be thinking, this all sounds nice, but it's speculative. We don't know if the multiverse is real. We don't know if other universes have different light speeds. We might be wrong about all of this. And you're right, we might be wrong. This is frontier science, the edge of human understanding. The ideas we've explored are our best current attempts to make sense of deep questions, but they could be overturned by new evidence, new theories, new insights. But here's what I want you to understand. Even if the specific models are wrong, the questions remain. Why does the speed of light have the value it does? Why are the constants of nature fine-tuned for complexity? Why does anything exist at all? These questions demand answers, and the multiverse hypothesis is currently our most promising answer. If it turns out to be wrong, we'll need something even more remarkable to replace it. And in the meantime, engaging with these ideas, really thinking about them, not just intellectually, but existentially, changes you. It expands your sense of what's possible, deepens your appreciation for existence, and puts your life in perspective. That's valuable, whether or not the multiverse is real. Let me tell you what I find most beautiful about all of this. We live in an age where humans are capable of asking these questions and making progress on them. For most of human history, questions about the nature of reality, the origin of existence, the structure of the cosmos, these were purely philosophical or religious. People could speculate, but they couldn't test, couldn't calculate, couldn't observe. Now we can. We can map the cosmic microwave background and search for collision signatures. We can collide particles at high energies and study vacuum stability. We can develop theories like string theory and eternal inflation that make predictions. We can use mathematics to explore the space of possible universes. We're still far from definitive answers, but we're making genuine progress. And you're alive to witness this. You exist at a moment in history when humans are grappling with the deepest questions about reality and actually making headway. That's extraordinary. Think about it. 1,000 years ago, nobody could have even formulated these questions properly. 1,000 years from now, they might be settled. But right now, in your lifetime, they're open questions, active areas of research.